So first let's look at the rule for the derivative of natural log. So if I take the derivative of the natural log of x, then that's equal to 1 over x, where x has to be greater than 0. Okay, you can't take the natural log of 0 or of a negative number. So we just have positive numbers that we take the natural log of. Well, this is just with x. So what about in general? If we take the derivative of the natural log of u, so of anything here, that's going to be equal to 1 over u times the derivative of u. Another way of writing this, if you ever see u prime over u, this means the same thing. du is the same as u prime. So it's the derivative of u over u. And of course, just like with this previous statement, u has to be greater than 0. Okay, so for example, let's say that I had y equals the natural log of x squared plus 4. And I wanted to take the derivative of this. Then the first thing you need to identify is your u. So your u is always what you're taking the natural log of. And so my u prime, or my du, is equal to 2x. So my derivative is 1 over u du. So 1 over x squared plus 4 times 2x, or 2x over x squared plus 4. Okay, let's look at one more example real quick. Let's say that I wanted to take the derivative of natural log of x raised to the 5th power. Alright, so my u is going to be whatever I am raising to a power. So my u is going to be the natural log of x. So then my du is going to be, well, what's the derivative of the natural log of x? Just 1 over x, right? Because it's 1 over u du. 1 over x times the derivative of x is just 1. Okay? So now, let's look back at this though. We need to be careful. Okay, we've got to be very careful here. So I have a u of the natural log of x, and I'm raising it to the 5th power. But that 5 is a power up there, so we have to be careful, because how do we evaluate this with the power rule? You have to say 5 times what's in front, and then we have to reduce the power by 1, and then we have to multiply by the du. Alright, so this is the derivative is equal to 5 times the natural log of x to the 4th times the du 1 over x. So you see, this problem was actually a little different than the previous problem. On the previous problem, all I had was the natural log of something. On this problem that I just worked out, I had the natural log raised to a power. And so the only part that I had to follow the definition for the derivative of natural log was over here whenever I took the derivative of my u. Other than that, it was just a chain rule problem where we had to use the power rule. Alright, so I have to be very careful whenever we take these derivatives and make sure that we follow all of our rules. Alright, now let's say that I had f of x equals the natural log of x times x squared plus 3 to the third power over the square root of 5x squared plus 1. So this is a problem like I was describing to you earlier, where if you're taking the natural log of an expression that is very complicated in itself. It has a numerator, it has a denominator. Look, it even has more than one term in the numerator, and then it has a power here, and then you have a radical in the denominator. Taking the natural log of something like this allows us to rewrite it using our natural log properties, or our logarithmic properties. And so before I do any type of calculus, I apply my logarithmic properties. So this function is going to be equal to, so the first property you always want to apply if you have a fraction is the quotient rule. So this would be the natural log of, and you may want to start putting things in parentheses to kind of separate, it's really up to you. The natural log of x times x squared plus 3 to the third power. Alright, and if I'm applying the quotient rule, there's the numerator, so minus the natural log of the square root, and let's go ahead and write that as a power. So 5x squared plus 1 to the 1/2 power. Now we're not done applying logarithmic properties. That was the first property. The quotient rule always, if you have a quotient. Alright, now we want to see, can we apply the product rule anywhere? And we can, because we have a product here. Alright, so this first term is going to become the natural log of x plus the natural log of x squared plus 3 to the third power. And then I have minus the natural log of 5x squared plus 1 to the 1/2. Now if you're having trouble rewriting expressions like this, you haven't practiced much with logarithms, you may want to look up expanding logarithms, because that's what we just did. We took a logarithm and we expanded it completely. Alright, well, we haven't completely expanded it, but we've expanded it pretty far. We have one more property to look at, and that is the power rule for logarithms. So now, if you have any power, once you've applied all of your product and quotient rules that you can, you take the power and move in front of the logarithm. So this is the natural log of x plus 3 times the natural log of x squared plus 3 minus 1/2 times the natural log of 5x squared plus 1. So notice I haven't done any calculus yet. I've just done algebra. Okay, so I've rewritten my function. Now, let's say that I wanted to find the derivative of this function. So now I start applying my derivative rules for logarithms. The derivative of the natural log of x is just 1 over x. Now look at this next term. I have 3 times the natural log of x squared plus 3. So x squared plus 3 is my u. And my du for this expression here is going to be 2x. So I have to remember, alright, first I have a constant in front, so that's going to go in my numerator. And then my formula for the derivative of natural log of u is 1 over u times du. So this is going to be 1 over x squared plus 3 times the du, 2x. Alright, we'll come back and we'll simplify this a little bit in a second. Alright, so that's the derivative of this expression, minus, I have 1/2 times, again, when I take the natural log of something other than just x, that's my u. So for this expression, my u is 5x squared plus 1. That makes my du equal to 10x. So 1 over u du, that's going to be 1 over 5x squared plus 1 times the du, 10x. Alright, so now my derivative is 1 over x plus, multiply across, that's going to be 6x over x squared plus 3 minus, multiply across, that's going to be 10x over, now I have a 2 down here, so you want to write that as 2 times 5x squared plus 1. Alright, so we use logarithms to help rewrite an expression, and then the derivative wasn't as hard as it would have been as if we would have just tried to take the derivative of this expression to begin with. However, notice this problem already had a logarithm in it. It had natural log. Well, how could we maybe use the natural log if it's not there? Well, as long as I think about something like this, or a problem as an equation, for example, let's say that I had just y equals x minus 2 squared over the square root of x squared plus 1. I don't see any logarithms in this expression. Now, if I told you to find the derivative of this, of y, then it's doable, but it would take you a little while. And then you'd have to worry about simplifying at the end and all of that kind of fun stuff. Well, using logarithms, what we can do, and this is a little different, so make sure you're paying attention. What we can do, if we think about this as an equation, we can take the natural log of both sides of the equation. Okay, and so what would the left side of the equation become then? The left side of the equation, if u is equal to my y, my du would then be y prime, the derivative of y. Alright, so the left side of the equation would be 1 over u du, or 1 over y times y prime. Alright, so it is y prime divided by y. That's what the left side of my equation is. Alright, now let me work with the right side of the equation. So the right side of the equation, I could then rewrite the right side first using my algebra or my natural log properties. So the left side of the equation, notice I put equals up here before I do any calculus. I'm just rewriting the right side of the equation. That's going to be equal to the natural log of x minus 2 squared minus the natural log of x squared plus 1 to the 1/2 then I can rewrite that using the power rule. So that's 2 times the natural log of x minus 2 minus 1/2 times the natural log of x squared plus 1. Alright, so how about I start taking derivatives here now on the right side. So for this first expression, my u is x minus 2. So my du is 1. So 1 over u du, and there's a 2 in front. So 2 times 1 over u, that's going to be 1 over x minus 2 times du, or times 1, minus 1/2 times, now for this expression my u changes. When I take the derivative, my u is equal to x squared plus 1, and my du is equal to 2x. So 1 over u, 1 over x squared plus 1 times du of 2x. Alright, so this is going to be 2 over x minus 2 minus, if you say 2 times 1/2, those cancel out. That gives you x over x squared plus 1. Now this isn't what the first derivative is equal to, because to have the first derivative, I'd have y prime equals. So if we still think about this like it's an equation, and we want to solve for the first derivative, then I need to get rid of this y that's in the denominator on the left side of my equation. To do that, you would simply multiply both sides of the equation times y. So if I multiply both sides of the equation times y, then that would cancel out, and I would have y prime equals 2 over x minus 2 minus x over x squared plus 1. And now what is y equal to? Remember, y is what we started with. If you go back to the very beginning, and I'll highlight real quick what I had before. I had y equals this right here. I didn't have any natural log or anything like that. And so where I have a y in my answer now, I want to plug in x minus 2 squared over the square root of x squared plus 1. So here where I have a y, I'm going to plug in this x minus 2 squared over the square root of x squared plus 1. So before multiplying that in, what I would suggest doing, since you have a minus here, is making all of this in here one term. Get a common denominator and just make one term here. So I'd have y prime equals, now my common denominator is simply going to be the product of these two denominators. That's x minus 2 times x squared plus 1. Alright, and so if you look at this first term, then you look at your common denominator, the part that you'd be missing is the x squared plus 1. So x squared plus 1 times 2 first goes here, minus, and then again, look at the common denominator, look at this denominator, the part that's missing is the x minus 2, so you say the numerator times x minus 2. Alright, and so we're just dealing with that part first. Now before I multiply this here in, I'm going to simplify my numerator up here. So go ahead and multiply all that out and see if you can put terms together. I'm going to multiply it out above it just to save a step for us writing. So that would be 2x squared plus 2 minus x squared plus 2x. All right. And so the numerator would now be x squared plus 2x plus 2. Alright, so you could probably do that not writing out as many steps as I did. You know, a lot of this stuff you can do in your head. I'm just trying to kind of work this first problem slow here and not skip any steps. So the calculus part wasn't too bad. It's really the algebra that's taken us the longest. And I purposefully did not multiply anything in because now that we have simplified as much as we can with the algebra, notice there are a couple things that we're going to be able to put together or cancel out here. This x minus 2 is going to cancel one of these x minus 2's out. So that's just going to become to the first power. And then whenever I multiply this x squared plus 1 in, that's the same as this term. So if I have this to the first power here and this to the 1/2 power, just add the powers, right? So in my numerator, I'm going to have x minus 2 to the first power times x squared plus 2x plus 2 over, now my denominator, again, just add the powers. That's going to be x squared plus 1 to the 3/2 power. Alright, so we can use logarithms to help us rewrite an expression so that we can take the derivative using the logarithm rules instead of having to go through all of the other derivative rules like Quotient Rule and stuff like that. Alright, so that is derivatives with logarithms, which most of you have already seen. You may not have seen that last part, but definitely want to practice those when you can. 1 over u du. Always remember that. 1 over u du. That's the formula that we want to use for the derivatives. Alright, so what about the integral of the natural logarithmic function? Well, if you remember back whenever you went over the power rule when taking derivatives, or the power rule when taking integrals, if you recall, if we tried to do this integral here using our rules that we are used to, using our rules like our power rule for integration, then I would rewrite this as the integral of x to the -1, right? And what would happen if I added 1 to this power? It will become x to the 0. So is this equal to x to the 0 power divided by 0? No, you couldn't do that. That was one of your restrictions. This power down here had to be I guess less than, this power down here would have to be greater than 1 in order to use the power rule. Alright, so, but we just learned that the derivative of the natural log of x equals 1 over x. And so if you know the derivative of something, if you know what the derivative of something is equal to, then the integral of that something has to be equal to what you started with. So the integral of 1 over x dx is equal to the natural log of the absolute value of x plus c. And so the reason why we have the absolute value is because, remember, we can't take the natural log of a negative number or of 0. Okay, it has to be greater than 0 there. So we must have some type of rule in general, because we're not only always going to have the natural log of x to deal with, and we do, the integral of 1 over u du is equal to the natural log of the absolute value of u plus c. And so as long as this du is present, that's the main thing. This du must be there. Then it's 1 over u. It's in the form 1 over u du. So the integral is going to equal to the natural log of the absolute value of u. So for example, let's say that I had the integral of 1 over 4x plus 5 dx. Alright, so whenever I first see this, in my mind, if I see a fraction, my first thoughts that I need to have are, is this a natural log integral? And the way that you can check that is, let the denominator be your u, take your du of that, and then if the du has a variable part, you would want to look for that variable part in the numerator. If the du doesn't have a variable, if it's just a constant, then make sure you just have a constant in the numerator. Alright? And so, as long as there's just a constant here, there's no other variable, then this is a natural log integral. So I do need to adjust for this constant. How do I do that? Bring out a what? 1/4. So now I can rewrite this as the integral of 1 over u du. Alright, and so we know that the integral of 1 over u du is the natural log of the absolute value of u plus c. Now plug your u back in. So this is 1/4 times the natural log of the absolute value of 4x plus 5 plus c. Alright, so let's say that I had the integral of x over x squared plus 1 dx. So the first thing that should pop into our mind is, I need to say, is this a natural log integral? So to tell if this is a natural log integral, let the denominator be your u. So u equals x squared plus 1. Then find your du. The derivative of u is 2x. So what I need to look for is, I need to see, is there an x to the first power in the numerator? Yes, there is. So as long as that variable part is in the numerator, now this is a natural log integral. So I come back, I adjust for my constant, so that's equal to 1/2 times the integral of 1 over u du. Notice whenever I've rewritten this thing, when I rewrite it, that I don't write my x there anymore. The x is contained in the du. Okay? So rewriting with this u substitution, the reason we rewrite is to make it simpler. And that does make it simpler. Alright, so that's equal to 1/2 times the natural log absolute value of u plus c. Or 1/2 times the natural log of the absolute value of x squared plus 1 plus c. Alright, what if I had the function y equals x over x squared plus 1 graphed, and I wanted to know what is the area below the curve, x over x squared plus 1, when I let x equal values between 0 and 3. Alright, so that would be the integral of x over x squared plus 1 dx. And if I want to know this area under the curve between x equals 0 and x equals 3, that makes this a definite integral. So this is the integral from 0 to 3. Alright, so now I've already worked out the integral, right? But I'm going to rework it out real quick. U equals x squared plus 1, so du equals 2x. That x is present, like it has to be. So I rewrite this as 1/2 times the integral of 1 over u du. And the integral, again, is evaluated from 0 to 3. So this equals 1/2 times the natural log of the absolute value of u, and that's going to be evaluated from 0 to 3. Now, a very common mistake, including myself, I've made this mistake, with definite integrals, when you get to this step here, if you put your boundaries here, it's very easy then just to plug them in. But remember, I don't plug in for u, I plug in for x in this problem. So I need to make sure that I substitute in my u so that I can have my x values here again. I've done it. I'm sure that there's lots of people out there that have done that. So make sure you plug your u back in before you plug in your boundaries. Alright, so this is 1/2. Since that's a constant on the outside, I'm going to multiply that back in at the end. So this is 1/2 times, now I'm going to plug in a 3. So that's the natural log of, that's going to be 3 squared, it's 9 plus 1, 10. So natural log of 10 minus, now plug in your 0. It gives you natural log of what? 1. Alright, now I don't know what the natural log of 10 is, but I do know what the natural log of 1 is. Remember, log base b of 1, regardless of the base, is always equal to 0. So the natural log of 1 is 0. So this is 1/2 times the natural log of 10. Because again, that right there is equal to 0. And so I could bring up a calculator if I wanted to find this area. I wanted to get an approximation. This is the exact answer, just natural log of 10 over 2. But if I wanted to get an exact answer, I could say I have a natural log button here. So 10 natural log times 0.5. Alright, and that's the actual answer, or this is a rounded answer here.
Why isn't it
Okay.
1 over ln of 1 over 10?
We got 1.151 about.